Think Engineering. Today we're going to be talking about reverse engineering, 3D scanning, designing for additive manufacturing, how they all kind of tie together. Um, so reverse engineering, when you're looking at a part and you plan to reverse engineer it, you got to make a couple considerations. For us, we have 3D scanning at our disposal. We have our Keyence here, and we have a hand scanner that we use for larger parts. Um, when I'm looking at a part and I'm trying to decide whether or not I'm going to be reverse engineering it, I'm going to be trying to decide, is this worth my time? Should I take it on the scanner because I'm going to have to post-process that mesh data? I'm going to have to do a lot of work with that. Is it worth my time or is it not? You're going to look at your parts, and you're going to have some parts that are simple, like this part. Uh, this is just a simple L bracket. It's made up of like 5 dimensions. I would never 3D scan this part. This is something you could simply just reverse engineer with calipers. Um, it's all parallel walls. It's a really simple part. Whereas, on the flip side, you got something like this mouse. This mouse is super organic. It doesn't have, it's got barely any flats on the entire part. There's no world in which I would ever approach this any other way than 3D scanning. You need to think about whether or not it's organic, if it's a feature-heavy part, whether, features on one end of a part and another feature, if they're critical, how they relate to each other. In the case of the mouse here, there's a lot of contoured profiles and there's multiple parts all coming together. That fit needs to be perfect, so you need to match that contour correctly or else you're not going to fit part to part. You might even have something like this part here, which is kind of a mix between. I could absolutely go ahead and reverse engineer this part with calipers. You could do that, but the benefits that you'd get from going through 3D scanning and reverse engineering off of your scan is that I know that I'm going to have good relation between my features. I'm going to be able to look at the part as a whole, and I'm going to make sure that everything is, correctly oriented in relation to each other as far as features go. You might want to consider the material of the part. 3D scanning doesn't work very well with some materials. If it's a rubber, if it's flexible, the part's not going to be holding its proper rigid shape while you're scanning it, and so your mesh body is going to be deformed. It might be something like a clear material that the scanner isn't going to be able to pick up very well, or something very shiny. You can still use spray. 3D scanning spray will help you deal with difficult to work with materials, but you want to consider that because it's an added level of difficulty to your part. Do you have good line of sight to all the features that go into your part? The scanner needs to be able to see everything. If you have deep pockets, you might not actually be able to get that data, and it might not be very helpful for you what you'd get from your scan. And this actually comes up a few times. Do you have limited time with the part? It's not uncommon to happen that a customer will say, hey, I have to pull this part off of our line, but we need to get it right back on the line as quickly as possible. Can you please get this back in our hands within the same day even? So I might only have an hour or 2 with the part before I got to give it back to them. That's where 3D scanning can come in handy, because I can get my scan and I could just be working off that scan the whole time. I don't need to have the part anymore after that. So in this case, we're actually going to be working on this base part of the mouse. It's not quite as complicated as the whole mouse itself, but it's still got lots of contours. It's got a couple flats, but generally there's no great way to orient this or to capture this contour that goes across the part other than having good reference geometry to refer to. So I'm going to go ahead and get this popped in our scanner. And we're going to switch over to our software. Yeah, so this is our VL700. I'm just going to get the part in there. I'm going to be just using some simple settings, and I'm going to go ahead and start scanning. Yeah, so this guy will, it'll put the part into one orientation, it'll capture some data, and then it'll just move it to the next position, and it'll get several different positions, and it'll bring all that point data together, and it'll make a mesh body for me to use. You'll have to capture the part from multiple sides. In this case, I'm getting a good top view. I'd want to flip it over on its other side and get the bottom, and then I'd want some kind of third orientation that ties them all together. Once I got those, I'd be able to go into the next steps where I bring them all together. Once you get enough data, you can have a complete scan of your part. Really depends on what you're trying to get out of your part. Sometimes you don't even need a full scan. You don't even need to consider whether or not it's watertight, which means that I've captured literally every part of this part. In the case of this part, I'm going to go ahead and get it all. When I captured the scan beforehand, I had taped the bottom of it. It's got this clear panel on the bottom side of it, and it's hollow. It's got ribs. It's an injection molded part. And so I just decided to cover that with masking tape, which meant that it's going to come across as a complete solid body. Yep, so just a little bit longer here. So with this part here, this is a really nice material to work with for 3D scanning. It is a dark matte black. That's pretty much the ideal material you have for 3D scanning. If you're working with something that is a shiny polished metal, something like a clear plastic, something bright like white or something like that, the scanner is going to have a harder time picking that up, and that's why we have scanner spray that will go ahead, which will kind of give it an even, consistent color and texture. So even some tricky materials are still 3D scannable. Yeah, so this is just going to be one part of the scan. I'm going to go ahead and wait for it right now. It's going to finish up. Right now it's meshing the body, so when it captures the data, it collects a bunch of points. It generates a point cloud. Once it's got all that data, it goes through automatically a process which will turn it into a mesh body for me. So here we go. This is the first scan, the scan we just took, and you can see it's got really good data of the top side of this part. Now, I've already gone ahead and gotten a full mesh here. So this is me having combined multiple scans together and gotten a complete scan of this part. Now you can see it's messy. It's in a messy state. It's got holes in it still where it didn't totally fill in. It's got some rough texture on some areas where maybe it didn't scan as well. I have stuff like the logos on there. I have just some bumps and artifacts, which might even be from the part itself. Got a line from the tape. It's also, what you can't see here, it's a lot of triangles. It's a pretty difficult to work with model. If I were to try to bring this into SOLIDWORKS, our modeling software, I'd have a very hard time managing my file because it would be a very heavy part file. I'd probably be lagging trying to do anything on this part. So this is where I take this part and I'm going to go through and do some post-processing, some cleanup to make it a more usable bit of data. So the first thing you're going to want to do is actually assign it a coordinate system where your world coordinates are, your X, Y, Z, so that you could bring it into any software and it's going to have that. Because right now, off the scanner, it's got a pretty randomly assigned coordinates. So those are not really going to relate to anything. If I were to bring this into SOLIDWORKS, I'd have no real way to align this to anything, any feature I was trying to make. So what I can do is I could just go through and start assigning some geometry to here, some reference geometry. I've already taken some time and looked at this part, and I know my instinct to this part would be to say, hey, this bottom surface should be the top plane, but I spent a bit of time looking at the part, and I could see that it's an injection molded part. It's got ribs, and those ribs are actually not perpendicular to this plane at all. They're perpendicular to this top plane. So when the part gets molded, I want to be oriented alongside this top plane. So I'm going to plan for that. I'm going to go ahead and just lay down a couple planes on the few flats that are on this part. I'm going to go ahead and grab this top plane, this bottom plane, and I'm even going to grab this little spot across here because I want to be able to figure out what the draft on this part is so I could use that while I'm doing my reverse engineering. So I got these planes. That's some good information right now. I want a few more things though. For one, I want to find the intersection line of these two planes so that I can go align perfectly to it. So I'm going to go ahead and say, give me some intersection lines. I have plane 4 and plane 5 here. So now I have this line that I could use. I'm also going to go ahead, nope, that's it for that. And then I'm going to go over here and I'm going to grab a couple angle dimensions because I want to be able to reference that. So plane 4, plane 5, those same two planes, I could see that I'm actually reading angle between those as 10.1. When you're dealing with a scan model, you know that you're dealing with a real world part. Parts, they warp over time, they have their own kind of manufacturing tolerance. I'm looking always for the design intent of the original part, the perfect CAD model that existed before the real world part was made. When I look at this 10.1 degrees, I know that the original designer who made this part likely was shooting for 10 degrees. Same thing here, I'm going to say plane 4 and plane 6 to see what this looks like. 93.2, that's telling me that they likely drafted this part to 3 degrees. So with that information now generated, I'm missing just one thing. For one, I'm going to go ahead and hide my angles. I'm going to hide all the planes except for that top one that I plan to use. So I have a plane and a line. Now I need a point. Plane, line, point is the best way to lock down your 6 degrees of freedom on a part, which is all I need in order to create my coordinate system. Now there's really no other features for me to grab on this part that would give me a good, what would become my front plane. So I'm just going to put a point right in the center where that logo was. So with these three, I'm now able to go in and generate a new coordinate system. I'm going to tell it. First, I'm going to orient it in the way that I want it to look when I bring it into my modeling software. I'm going to say that we're going to use plane 4. We're going to use intersection line 3 and point 2. And I'm going to say this is my ZX. This is my Z minus. And that's perfect. That's usually what I'm looking for. X is left to right, pointed to the right. Z, front to back, point to the front. And Y, pointing up. So with that, if I were to show my coordinate system, it's now exactly where I want it to be. When I save this out as an STL file, it's going to use this world coordinate system as where to orient this part. Okay, so now that it's oriented, I'm going to save it out as an XTL, and I'm going to bring it into what we use as Geomagics Essentials. There's a lot of other ways to do this. This is just software we use, and I'm going to have cleaned it up. So when I brought it in here, this part probably started out 3-5 million triangles. It was a pretty heavy part. If you were to see what that mesh looked like, it's kind of jagged and all over the place. It had holes, it had defects, it had stuff like that. I went through, cleaned up the part. You look at the edges of the part when you zoom in. This is a nice uniform distribution of triangles. I've remeshed it, I've decimated it, I've gotten those triangle counts down just to make it a nice usable part. I've patched all the holes, so this is now a watertight mesh, which is going to be really critical when I go into my modeling software. That's going to allow me to do stuff like hybrid features because it's going to treat it like a solid body. That I could do cuts, I could do extrudes, I could do all that to this body so long as it's watertight when I export it. It's also going to allow me to do stuff like section views, which is going to be really useful for another part we'll talk about in a minute. So once this is cleaned up, oh yeah, I also defeatured the logo too. It's something you could do. You could just go through, defeature some parts, some features on the part. Really easy to do. So go ahead and kind of get this to a nice clean model that I can now use in SOLIDWORKS. When I import it into SOLIDWORKS, this is what I get. Get a nice model to work with. Nice simple mesh, and if I look at my planes, it's right where I put them. And if I go into front plane here, you can see that the angle of these two faces is perfectly aligned to my front plane. So it's going to be really easy to do stuff like cuts or extrudes. I'm going to be able to get that information really easily. And just to validate what I was saying before, if I go through and do a draft analysis, and I set it to my top plane, I'll lower the tolerance on that, I can see that that seems really nice across the whole side. And if I try to read, I'm holding around 3 degrees, which is exactly what we saw when we measured that one wall. And you could even do draft analysis on a mesh body. You don't have to have a solid. Yeah, so when I have this part in this state, I got to think about, what is the effort that I want to put in towards reverse engineering? What am I trying to get at with this part? When we're designing for additive manufacturing, we got to consider what kind of technology we're planning to use and what kind of design constraints go along with those parts. What kind of requirements do parts like that have? And what are the things to make sure you hit, make sure you avoid, stuff like that. So here's just a couple examples of additive manufacturing. We've got multi-jet fusion, or maybe it's SLS. We've got FDM 3D printing, which I think we're all pretty familiar with, and even SLA 3D printing, resin, stuff like that. Most of these 3D printing technologies are going to be very similar to injection molding, where you want to try to maintain consistent thin walls. You need stuff like ribs, you need features like that. In the case of SLA, you probably want to consider how you're going to drain it, stuff like that. But in this case, we're actually going to be reverse engineering this part for FDM 3D printing. The good thing about FDM 3D printing is it just really doesn't care about thin walls or thick walls. It's not going to warp. It's not going to give you the same kind of issues you would have with other manufacturing methods. And so I know the original part had a bottom cover plate. It had shelled, it had ribs and everything. In the case of this part, it's really not going to be critical. It's also got 3 pockets on the inside that I know house magnets. So those will have to be incorporated somehow. So hopping back over to SolidWorks. One solution you could do with this is if, the part I'm trying to make here, maybe I really just need something that I can get on a table, something that's a quick interpretation of the part. Maybe I don't need this for high production. I just need a nice simple part. I want to go right off this mesh. And, if I was doing something like multi-jet fusion that doesn't have to be on a build plate, it doesn't need support material, I could get away with just sending the part as it is right now. But in the case of FDM, I know that a big requirement for that is that it's got to sit down on a build plate. It needs a really nice, clean, flat surface. And right now, this is not flat. If I look at it right now, it's got bumps, it's got high points, and even when I go through and try to line up where I want that sketch to be, I could see that like the thin area kind of warped upwards a little bit. So I'm going to want to give this a nice parametrically modeled base so that it's got a flat to use. So I could go through, I could build this sketch. This sketch, I use that 10 degrees that we found from our scan. We know that we're going to be using a 10 degrees here, and I line it up as best as I can, and I make sure to cut the underside so I don't have anything below that. I'll use that sketch line to get myself a plane, and then I'll go through and sketch out a profile. Now this profile is, the majority of the time that goes into building this part is trying to match this as well as I can to the CAD. Now this is not made up of simple arcs and lines. This is a lot of splines and a lot of, compound arcs as well, that I do want to make sure this sketch has tangency across all of my lines. And so I went through, spent the time, made a sketch that goes across it. Now there's areas where I'm going high on the part, there's areas where I'm going low. I actually got 2 right next to each other there. I'm not too worried about that. Right now I'm trying to just get my best interpolation of the profile of this part. From there, because I know this part's drafted, I made a point to maintain tangency across all those arcs, and I can go ahead and do a very simple extrude upwards with a pretty extreme draft so that it pushes into the mesh all the way along. Now this is not clean, this is not perfect, but it doesn't give me any hard lips and it gives me a perfect bottom. So right now I could absolutely save this out as an STL and run with it. This could be a FDM print right now. So that's one solution you could do with the part. I tend to think that it's best to just go through the full effort and reverse engineer a part, but a lot of times you don't need that. It depends on what your project is, what it is that your requirements are, and this is a really solid hybrid approach to get you to a usable model. But if I were to just want to say, okay, well that's all good and all, but I really want to get myself a fully reverse engineered parametric part, you can just use that. You could use your model here because I've already gone through, I've decimated it, I've made it a clean, manageable file. I could spin this around freely, I could work with it really nicely, and I'm not going to have any problems manipulating it. It's just a really nice foundation to just go through and reverse engineer over top of. I've already established that base sketch, and I'm going to use that same sketch and extrude upwards to my top plane, which I've already established to be the top of the part, and I'm going to use that 3 degrees we found earlier, and you can see it totally matches our part great. We have our transparency. You can easily flip those transparencies to get different views on it and try to understand, how well am I matching my geometry. In the case of here, I could even see some built-in design intent to this part. These 2 nubs on the top of this brim that goes over part of the area, totally aligned to the front plane. They made it nice and perpendicular to this angle here. Really nice and useful for me because I know that when I go through and I extrude up that brim and I cut across, I can make my sketch and I know that it's, the design intent was clearly that this one profile is used to cut across both sides. So I match it as best as I can. You can see there's, it's a real world part, so it's not going to match perfectly. I get something that's as close as I think is necessary, and I cut it across. A little bit of cleanup. I could even put some fillets across there because I know that's part of it. And because I have my mesh here, I'm able to see that I'm matching those radiuses pretty good. And with that, I have pretty much the part reverse engineered outside of any of the shelling or the ribs on the underside here. At this point, I don't need my mesh anymore, so I could go ahead and clear my scan away. At this point, I would go to my calipers. I would take real world measurements because this is the stuff that's all kind of, it's hidden, it's underneath that plate, and so I can go through and kind of figure out what I need to do with that. I know that I need those pockets for some magnets, so I'm going to go right ahead and cut those magnet pockets in there. I know what the off-the-shelf sizing for this magnets was. I think it was a 3/8 by 3/8 by 16 magnet. So I got those pockets right where they are in the part, and now this is ready to go. From here, I can just 3D print the part. You can see I did just that. Having a nice flat bottom, this was a totally makeable part. I was able to print it on our FDM machine, and it fits the mouse just right. I got my profile exactly as the original part was. If you want to even take it another step forward, obviously I designed it for FDM, but just as easily, I have the information here. I have all the geometry I need. I can just take this part all the way, make it an injection moldable part. It's just a few more steps further to be able to give it the lip for the plate, the ribs, make sure that I size those ribs appropriately for the wall thickness of this part. I know what the wall thickness is. I can take calipers to it and find that really easily, and it's just a really simple matter to take it the rest of the way and make an injection moldable part, which of course if I'm doing FDM printing wouldn't really be my priority here, but say I wanted to make it for multi-jet fusion or even SLA, a lot of the same design requirements of the injection molded part work very well for those technologies, so I would want to probably take it the full step anyway, give it nice ribs and all that. Yeah, so being able to just take it the extra step and get it to an injection moldable part, I'm able to give it ribs, I'm able to give it the pocket, even able to model in a bit of reference geometry for myself. That plate, if I needed to go and get that plate laser cut, water cut, whatever, could do so because I have that built in here now. Put the magnets in. I noticed they only used 2 out of the 3, but all 3 pockets are there regardless. You could use any combination of them. And yeah, that is a fully reverse engineered part built off of 3D scan. Yeah, so just to review, going through the process, I'd get individual scans, I knit them all together to get one complete scan. I'm going to go through, I'm going to orient it into the world, I'm going to get it a nice coordinate system, I'm going to get any kind of reference information I want off of that scan first if I can, because being able to measure that stuff in the scan software is a lot simpler than taking it in SOLIDWORKS and trying to figure that out. And then I'm just going to go through the process of cleaning up my mesh and get it to a nice usable state. Once I have it in there, take it into SOLIDWORKS and I do whatever level of reverse engineering I need over top of it, really depending on what my requirements are. All right, at this point, we could talk about any questions anyone has, or we could jump into a little bit of additional techniques. I got another model here where I do some hybrid modeling, some really useful approaches when you just need to control a couple key features. Does anyone have any questions? All right. Yeah, so we're just going to jump over to different scan. Yeah, so same thing. When I got my individual scans, knitted them all together, got myself this nice complete scan, and I made sure to orient it into my world. So it's got coordinates exactly where I would expect them to be. I make sure that in the case of this part, what's super critical to me is that I have symmetry. So I have my nice mid-plane established, which I did by just grabbing these 2 planes, and I found the mid-plane between them, which is going to give me a nice controlled mid-plane across the part. So I use those to establish a line, which is what I used to orient my part. So same thing, I'm going to take it into GeoMagics here, only for this time I'm going to do something a little bit different. So I actually want to leave with two different parts. So give me just 1 second. Yeah. So gonna bring it in here, still gonna go through, gonna clean it up, make it nice and clean. I'm gonna save this out. Once it's clean and reduced down to a usable triangle count, I'm gonna save it out as a new STL. But then I'm gonna do one additional step where I'm going to do a save as operation, and I'm going to defeature some of these key features that I want to take control of. So I'm going to make a second version of this part where I've defeatured the holes in the mounting hole locations here, and I defeatured this major cylindrical pocket that goes through the middle. If you look at it, I've cleaned it up. I've made it to the point where this looks like a nice, clean, flat plane. You wouldn't have known that there was originally holes there. So I save out both STLs, and because I've already established the world coordinate system on both of those parts before I did this process, when I go into SOLIDWORKS and I import both of those mesh bodies, they're going to occupy the exact same space as each other, which is really useful for me. So the first thing I'm going to do is I'm going to just be looking at the non-defeatured part, and I'm going to give myself some reference sketches. So I'm going to go through, I'm going to just sketch up, I'm going to find what my hole pattern looks like. I really want to know a nice controlled version of, what is this hole pattern? How does it relate to my main feature here? I know that I want these 4 pockets to be controlled in a way that's related to this major pocket here. I'm going to get a couple things here that I'm mostly just using for reference, for my reference. I'm able to see that these holes, it's just taking screws to it to figure out what they were intended for. I could tell that they're clearly intended for a number 10 screw, so I have that information in my pocket. I'm also going to take the time to create this sketch for the revolve cut on this feature. And the great thing is, because I made this a solid body by making it completely watertight, they came in as solid bodies, I could go ahead and take a section view of this part and get just really good reference information to see while I go through and I make this sketch. I could see this information really well, and I could go in and line up my lines as close as possible, and I could find out what those dimensions ought to be. Now, the thing with this part is I want to be able to control a couple of these features. I really don't care about a majority of this part. It can be as messy and sloppy as it needs to be. That's really just mass. That's just mass. Having those ribs there, it doesn't matter if those are sharp or a little bit wonky. They're still doing their job. Most of this geometry is just going to be doing its job no matter what. What I really want to be able to control is those 5 holes. So I want to be able to change the size of those holes freely. I need to be able to downsize them, upsize them, modify them in whatever way I want. And I really want to have control over this pocket, which is clearly the key focal feature of this part. There's a world where I want to intentionally undersize that hole so that we can go through with our CNC mill and remount that hole to a tight controlled tolerance with a nice surface finish. There's a world where I want to be able to control the fit of that pocket so that we can have either a slip fit, interference fit, what have you. So I am going to go ahead and put those features back into the part as a hybrid model. So I'm still dealing with a mesh body here. If I switch to this view, you can see that I'm still talking about dealing with a mesh body. But I'm going to go through, I'm going to delete my reference mesh because I don't need that one anymore. I've already made my sketches, and I'm going to go through and I'm going to repunch those holes using the sketch here. So they're positioned correctly with that, and now this is a hole wizard feature. I can go into this feature at any time and change the size of those holes as I see fit. I set it to be for loose fit number 10. I could just as easily go ahead and change that to a close fit if I want, downsize it to a number 8, whatever I want. And just as easily, I have this sketch already established. I can go ahead and do a cut revolve across the part. This is now a nice controlled feature. And if I go to my line view, you can see that these are surface faces. So this is made up of surfaces, surface geometry. It's still a solid body, but now this is a hybrid part. This has surface geometry and mesh geometry in it. The really cool thing about having a hybrid part like that is a couple new features open up to you. You could actually put fillets on a part like that where those two kind of surfaces meet. You could throw a fillet or a chamfer on those. You wouldn't be able to do that with just a straight mesh body. So you got a bit more control over your part. But I didn't have to go through, I didn't have to reverse engineer it. I just had to make 2 simple sketches, and I'm able to take control of the features I actually care about on this part. So it's a really useful technique. And I know this part's a bit simple, but there's all sorts of times where I need to reintroduce my holes to a mesh scan, just because a lot of times, these, I'm talking about thin holes that I got either clear line of sight or they're through holes. Oftentimes the holes on your part are blind or they're tapped, and what you're going to get off of your scan is going to be messy or pretty unusable. So a lot of times the best quality you're going to get is if you could go ahead and take the little bit of extra time it takes to defeature those holes and reintroduce them in a nice controlled way. You can get them perfectly cylindrical and exactly the way that you need them to be, and have control to change them down the road. That's it for my presentation. Does anyone have any questions at this point? All right, well, I've been Connor with Interlink Engineering, and thank you guys for coming out.